Okay, so these notes are actually going to be set up a lot like 6.7, where we're going to discuss this first page, and then we'll do a couple examples together. So our goal for today, you will want a piece of notebook paper for the examples, because you'll notice the assignment is actually just on the back of this. So you'll want a piece of notebook paper to take examples on after we finish discussing the front side of this. So our goal is to identify possible rational zeros of a polynomial function, and then to find all the rational zeros of the polynomial function. Basically, what this goal is saying is that we are going to be able to solve polynomials. Now, the way we've been solving polynomials, if it's anything with a higher degree than 2, meaning a quadratic, we've had to solve by factoring. That's still going to be the case of how we're going to kind of approach these. The rational zero theorem. If a polynomial function, if p of x is a polynomial function with an integral coefficients, meaning counting numbers, so that's numbers like -3, -2, -1, 0, 1, 2, 3. Okay, those are counting numbers. Okay, so if our polynomial, all of our coefficients are counting numbers, which you'll notice most of the ones that we've been dealing with this unit have been. Then every rational zero, okay, so the zeros that are real, that are rational numbers, meaning fractions, which also include our counting numbers, like integers, okay? So if we have the solutions that are fractions or can be written as fractions or are counting numbers, then every one of those zeros, those solutions of this polynomial, is in the form of p over q, in the form of a fraction. A rational number in simplest form, where p has to be a factor of the constant term and q is a factor of the leading coefficient. Okay, so let's look at an example. Here we are given a polynomial. This is the general polynomial. This would be a number x to a power plus, this is a number x to the next power plus dot, 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 all the way until you have a number x plus a number. Okay? It says that the p, the number on top, okay, so the form that our solutions are going to be in, p has to be a factor, p being on top, has to be a factor of the constant, so this number here at the end. This might sound like Chinese right now, or gibberish, or some foreign language, okay? But we'll get there, I promise. All right, so given this polynomial, p has to be a factor of the constant, okay? And q has to be a factor of the leading coefficient. That's what this last sentence says. Okay, so let me highlight, we'll coordinate this. So p is a factor of the number there at the end, and q is a factor of this number at the beginning. Okay, so any possibility of the roots are going to come from this list of it has to be written as p over q. Okay, factors of the constants, p is a factor of the constants, over the factors of the leading coefficients. So let's actually make sense of what this is saying then. Okay, it says find all the possible roots for this polynomial. Okay, that means roots are solutions, so possibilities of solutions would then have to be factors of the constant, so here's your constant, over factors of the leading coefficient, here's your leading coefficient. I'm going to write that in. I just wanted to make it so that we were highlighting it also. So factors of 6 over factors of 3. So then what we have to do is we have to find all these factors. So we're going to make a list on the top of our fraction, and we'll make a list at the bottom of our fraction. So on the top of our fraction, the factors of 6 would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All of these numbers go into 6. Now I have to think about the positives and negatives. So 1, 2, 3, and 6. The factors of 3 are just 1 and 3, so positive and negatives of 1 and 3. Okay. So now what we're going to do is we're going to come up with all the possibilities that is made up, all the combinations that's made up from these of fractions that can be made up of this number on top and this number on the bottom. Okay? So the first one I would do is 1 over 1, which is 1, so plus or minus 1. The next one I would do is 1 over 3, so plus or minus 1/3. The next one I would do is 2 over 1, which is positive or negative 2, and 2 over 3, which is positive or negative 2/3. I'm just going through and making this list. The next one would be 3 over 1, so positive or negative 3, and 3 over 3. But wait a minute. 3 over 3 is 1, which we already have in our list, so we don't have to write it again. 6 over 1 is 6, and 6 over 3 is going to be 2, which 2 is already in our list, so we don't have to add that one. So this list right here, these numbers are going to be the possible roots. Now, it doesn't mean that all of them are roots, okay? But if this polynomial has zeros, which it should have 3 solutions, if they're real and they are rational, then it would fall in this list. So one of them would be in that list, okay? But you can check that. We could verify. We could plug in 1 and see if it's a 0. We could plug in negative 1 and see if it's a 0 to see if they are solutions to this polynomial. We could plug in a third. We could plug in negative 1/3. So we'd have to test to figure out which ones are actual roots. These are just our possibility of roots. Okay? So what the corollary says is that if we have a polynomial and the leading coefficient is 1, okay, so that number out front is 1, the leading coefficient is the bottom part, so we would be looking at factors of 1 here, and a non-zero constant term, so our constant term cannot be 0, then any rational zeros must be factors of the constant term. So what it's saying is, if this is saying factors of 1, then when you divide by 1, none of these numbers change. So if this wasn't an option, if this was 1, our options would just be positive or negative 1, 2, 3, and 6. Because 1 over 1 is 1, and 2 over 1 is 2, and 3 over 1 is 3. That's what this corollary is saying. But that only works if your leading coefficient is 1. So we'll do it with this one here. All right, so our possible roots. We're going to come up with that list right here. Okay? Now, when we go, you can always think about it like this. So we would have the factors of the constant on top, and we would have the factors of the leading coefficient on the bottom. So the factors of 42 and the factors of, in this case, this leading coefficient is 1. And that's what I was saying. You can always write it out like this, but this corollary tells us that our answer for possibility of roots are just going to be the factors of 42. Because if I write out this middle step, the only thing on the bottom is positive or negative 1. But on top, we have positive or negative 1, positive or negative 2, 3 goes into it, and 4 doesn't, 5 doesn't, 6 does, 7 does. The next one would be 14, then 21, and 42. Okay, so when we write our list, this is actually going to be our list, the top there. So our possibility of roots is just going to be the plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 7, plus or minus 14, plus or minus 21, positive or negative 42, and these are going to be our possibility of roots. Okay, that whole list right there. So what I want you to do right now is I'm going to pause the video, and I want you to find an actual root. or an actual 0. So plug in 1 or plug in -1 and see if it is a 0. If we plug it in, do we get 0? Okay, so I want you to try right now and figure out which one is going to be an actual 0 of this. Okay, so what I found was an actual 0. One of the actual zeros was 2. Now you might have found a different one, and that's okay. We'll all get to the same spot. But for the purpose of taking notes, I'm going to go with the actual 0 being 2. If I plug in 2, which I did here, 2 to the third minus 6 times 2 squared minus 13 times 2 plus 42, I get 0. So I know that 2 is a 0. Okay. What this also tells me, though, is that I have a factor, okay, because I know x is 2. That's one of my solutions. That means that I have a factor of x minus 2 equals 0. And I can see then that that is a factor of the polynomial. So this is actually just branching off of what we did in 6.6, where I gave you a factor and said, given this polynomial and a factor of x minus 2, factor this polynomial completely. Well, I'm not giving you the x minus 2 this time. Instead, you're using this information to find a 0 to say, yep, x minus 2 is going to be a factor. So then what we're going to do is, now that we know x minus 2 is a factor, we have to start by factoring it out. We can do that using synthetic division. So we're going to put a 2 in the box. Make sure your degrees all line up, 3, 2, 1, 0. So this is a 1, -6, 13, -13, sorry, and 42. Bring down the 1. Multiply by the box. 1 times 2 is 2. Add up -6 and 2. You get -4. -4 times 2 is -8. Add up -13 and -8, you'll get -21. -21 times 2 is -42. And when you add up -42 and +42, you get 0. Now, we need it to be 0 because we said that has to be a factor. That's why we chose it. It needs to be a factor. So what this tells me is that if one of my factors is x minus 2, and I divide that out, x minus 2, what I'm left with is 1x squared minus 4x minus 21. From here, you still have to factor it completely, okay? I should make it a polynomial because I need to find the zeros of this polynomial. So there it is factored, it's set equal to 0. I have to continue factoring this because I want to finish solving this polynomial. So I have x minus 2, and then I know that this quadratic is also going to factor, or I'm hoping that it factors. If it doesn't, technically I could use quadratic formula to solve and find the other 2 zeros. But I'm pretty sure that all these ones they'll factor completely. So I break this one down into x and x. What multiplies to -21? Do a couple different trials here. I'm probably going to go with 7 and 3. My outside would be 3x. My inside would be 7x. I know one of them has to have a negative sign. -7x and a positive 3x will make -4x. So there it is factored. That is the factored form of this polynomial. That means that our solutions then are x equals, remember you could take x minus 2, set it equals 0, x minus 7 equals 0, and x plus 3 equals 0, and solve for x on all three. But I know that it's going to come out as x equals 2, x equals 7, or x equals -3. Now you'll notice that all of these are nice numbers, okay? And if I look, they're all in my possibility of roots. So if you don't start with your actual 0 being 2, maybe you started with your actual 0 as 7, it just changes how your work looks along the way, but in the end, you'll still have this as your factored form. If you found your actual 0 as -3, again, your work would change, but your final answer and your factored form in the end would still look the same, except for maybe you wrote these in a separate order. Okay. So we're going to try one more problem together, and then you guys will have the rest of the time to work on the assignment. Okay, so here's what your problem is going to look like. It's going to say to find all the possible zeros, write the polynomial in factor form, and find the actual zeros. So you might need to hit pause so you can write this down on your notebook paper and the problem. And then if you look up, or look, I guess, down, the rest of the problem here is you're going to be given the polynomial. You're going to have a spot to write the possible zeros. You're going to have space to do all your work. Write it in factored form, and then find all of the actual zeros. So you're solving it completely. Now, it really doesn't matter here. It is technically set equal to f of x, but it'd be the same as if this were to be set equal to 0, and we're finding the solution. So if you want to change it so that they're set equal to 0, if that makes more sense to you, then think about it that way, okay? But it has to be an equation, technically, to have roots or zeros or solutions. So it has to be set equal to something. It doesn't matter if it's f of x or 0 here. So our possible zeros. Remember from the front side of our notes that we're looking of factors of a constant. So this number here, 12, over the factors of the leading coefficient, which in this case is 2. So that's going to be our possibility of zeros. So factors of 12 over factors of 2. So I made your assignment a little bit easier, and the 4 problems on your assignment have leading coefficients of 1, so it narrows down how many possibilities there are. So this one is going to be a little bit trickier than the ones that are going to be on your assignment. So let's list our factors of 12. We have 1, 2, 3, 4, 6, and 12. The factors of 2 are just 1 and 2. So now let's come up with our possibility of zeros. 1 over 1 or 1 over 2. So positive or negative 1, positive or negative 1/2. 2 over 1 or 2 over 2. So 2 or 1. Positive or negative 2. 2 over 2, though, is 1, which we already have on our list. 3 over 1. Positive or negative 3. 3 over 2 is not there yet, so let's put that in. 4 over 1. 4 over 2 is 2. It's already on our list. 6 over 1. And 6 over 2 is 3. That's on our list. 12 over 1. 12 over 2 is 6, which we also have on our list already. Okay, so that's our first step, is find all the possibilities of zeros. Okay, the next step is to find one actual zero. So this would be a good time to pause the video and find an actual zero. I tend to try and do the whole numbers first and not worry about the fractions. So I'll try positive or negative 1, positive or negative 2, positive or negative 3. Then if I have to go back and find the fractions, I'll eventually do that. But I believe 2 was the first one that I found. So I know that x equals 2 is an actual zero. Okay? So that tells me then that the factor that that came from is x minus 2 equals 0. All right. So when I go to factor that out, notice that your degree started a little bit higher this time than our last example. It started as 4th degree. So that means we're supposed to be looking for 4 actual zeros. Okay. So when we go to factor this out, we're going to do synthetic division, like we've been doing. It's just the easier form of dividing it out. So I'm going to put 2 in the box. My coefficient is 4, 3, 2, 1, 0. I have a 2, 5, negative 11, negative 20, and 12. And I bring down the 2. Now I'm going to take that 2, multiply by the box, add them up, multiply by the box, add those up, multiply by the box, add those up, multiply by the box, add those up, and I'm looking for that remainder of 0 because what I'm working on is I'm factoring what I had, okay? So this is what I started with, and I'm factoring out x minus 2. What I have left is 2x to the power of, this is 0, 1, 2, that's a third degree, plus 9x squared, plus 7x, minus 6. That means we're going to have to find another 0 because I don't know how to factor something to the third degree. Okay, so I factored out the x minus 2, but I still have a third degree left. So I found that x equals 2 was an actual 0, but maybe someone else found that x also could be negative 2. Because that was another possibility. And that's why I said it's okay if you find more than one, because in the end, you might need them, okay? And it's a way for you to double check at the end that your actual zeros show up down here. So x equals negative 2. That factor would be x plus 2 equals 0. Okay, so now I'm going to take what I had left, this, and I'm going to divide out the x plus 2 from this portion here. So I have in my synthetic division, the box is now going to be a negative 2. I have 2, 9, 7, negative 6. And we're just doing synthetic division again. Because I know I started with the x minus 2, and I'm going to factor out also x plus 2, that's what I'm working on right now, and then I need to figure out what is still left after I factor out that x plus 2, okay? So that's what we're doing. So we get a 2 down here, multiply by the box, add them up, multiply by the box, add them up, multiply by the box, add them up. So what we have left, 0, 1, 2, is 2x squared plus 5x minus 3. So now we have our two factors at the beginning, and we have a quadratic. Now here you can still factor that further, or at least try. Sometimes it's not factorable. Okay, so we're going to try to factor it further. So we have the x minus 2, we have the x plus 2, and we're going to try to factor this further. What times what will give us 2x squared? A 2x and an x. My last times my last has to multiply to negative 3. So here's where you're going to have to do a little bit of trial and error. Maybe you have a positive 3 and a negative 1. Try it out. Your outside would be minus 2x. Your inside would be plus 3x. And that doesn't seem to work because that's going to give me 1x, which doesn't work. Okay, let's try and switching the location of the 3 and the 1. Because remember, that is going to matter when you have a 2 in there. Alright, so my outside is now negative 6x. My inside is 1x, which gives me negative 5x, which is pretty close, but just the sign is going to be wrong. So that means that my signs are wrong. So this would have to be the negative and that would be the positive. Let me try this and just double check. My outside is 6x. My inside is minus x, which does get me 5x. My last is negative 1 times 3, which does give me negative 3. So that appears to be factored correctly. So just a little trial and error to make sure you factor it correctly. So my factored form of this polynomial, and again, I don't care if you set it equal to 0 or set it equal to f of x. Whichever you want, it does not matter to me. So your factored form of this polynomial is x minus 2, x plus 2, 2x minus 1, and x plus 3. Okay? Now, I have to write out all my zeros also. So I already found that my 0 here, x minus 2 equals 0, turns into x equals 2. This one, x plus 2 equals 0, turns into x equals negative 2. This one, if you want to write them out and solve it, you can do it that way too. This last one will be x equals negative 3. So here you can see that you have 4 solutions, which is what we were aiming for with a 4th degree. And we can see that that means that our 4 solutions are all written as 4 factors also. So that's another additional example. There are 4 problems on the back of your assignment. And as I said, it was nice because the leading coefficient are 1. So it makes your possibility of zeros a lot less than a big giant list. It also means you won't have any fractions because they're just going to end up being the list of factors of this over the factors of 1. Well, the factors of 1 are just 1. Okay? So you're going to do the same thing that we did here. Now, this one is a 4th degree, so you're going to have to probably do synthetic division twice, just like we did before. This one's a 5th degree, so you might have to do synthetic division 3 times here. This one's a 3rd degree, so probably just once. A 4th degree, you're probably going to have to do synthetic division twice here. So you just have 4 problems. You should be able to finish it. If you don't, that is your Friday work this week.